Hello. So I see another message here to fair technology adoption. Yeah, okay. Hi everyone. Good morning and good afternoon in Australia, Melinda and other attendees from there. So very happy to have you here to on this session on domain ontologies for manufacturing and supply chains. So in this session we have three. Let me also share my screen. Very good. So before we start with the presentation, just some housekeeping, just so the ones that you have attended previous sessions, so you are familiar with that. So there will be a recording of this session that will be published, and also the slides will be shared on the page of the event. So please consider that your microphones and cameras are automatically deactivated. And after the talk, so in the discussion, please ask your questions in the Q&A function and other comments, etc., in the chat. In this session, we have it is about industrial domain ontologies. So as in Ontology Commons, we see we need various levels of ontologies in order to achieve interoperability from top level to middle level to domain level. So, and we have reference ontologies. So in this session, we have the objectives. What are the understanding about the requirements and specification of various domain ontologies. One is industrial maintenance. Then we have let's say, the challenge or the topic of system engineering, because it seems everything is a system. And also we have a talk about the reference ontology, a domain ontology in supply chains. So these topics will be presented and discussed by three speakers, which are all active in the Industrial Ontology Foundry. So first we have Melinda Hodkiewicz from the University of Western Australia. Welcome, Melinda. She will talk on modular ontologies for maintenance texts. So then Jinzhi Lu from EPFL, from my team here in Switzerland. So Jinzhi will talk about system engineering aspects as the foundation for industrial domain ontologies. And then Farhad Ameri from US, from Texas State University. Welcome, Farhad, also. He will be talking on the reference ontology on supply chain, procurement, and logistics. So I think without going spending more time on that, I would like to invite Melinda to take the floor or the screen. So Melinda Hodkiewicz is graduated with a bachelor with honors in metallurgy and science of materials from Oxford University in 1985, and then a PhD in engineering from the University of Western Australia in 2004. So it's a long period between bachelor and PhD, but in the meantime, Melinda spent good time in operation and maintenance roles in the mining industry in the USA, Australia, and the UK. Also in 2016, she was awarded the MESA Medal, a Lifetime Achievement Award for services to asset management in Australia. And in 2019, she was made a Fellow of the Australian Academy of Technology and Engineering. Since 2018, Melinda is involved in the Industrial Ontology Foundry, and there she coordinates the working group on maintenance. So Melinda, I will stop sharing, and I invite you to share your screen and talk. Thank you.
Thank you very much, Dimitri, for that and for organising the session and what I think has been a really great conference. Although it's been late in Australia, I've been absolutely glued to my screen, as I'm sure we all have. So thank you very much, everybody. I'm going to talk to you about modular ontologies for maintenance texts. And I'm going to start by really trying to frame the problem as I see it, as somebody who works very closely with manufacturing and resource and infrastructure companies that own a lot of assets, and they have a lot of maintenance-related and repair-related data. Just for some examples of the sorts of data that we are applying ontologies to and seek to apply ontologies to, things like maintenance work orders, inspection results, procedures, safety records, equipment manuals, failure investigations, operational shift reports, and equipment rebuild reports. Now, all of these are characterized by containing a large amount of unstructured free text data, kind of like I'm talking to you now, and also semi-structured data. So that's, you know, choosing from lists and drop-down menus. So what our focus has been at our group at the University of Western Australia, which is called the NLP-TLP group. TLP stands for Technical Language Processing, and you're going to hear me use that word quite a bit. What we are trying to do is to actually start with these raw texts. They contain enormous amounts of valuable industrial information, and right now they're largely processed manually. So what I'm going to talk to you briefly about is this pipeline of text annotation, training, so that we can recognize unseen texts, doing this on industrial data, and then the potential role, the actual and potential role of ontologies in being able to do certain value-adding tasks to this machine processed text through reasoning. So I'm going to concentrate in the short time I have on maintenance work order data. So maintenance work order is kind of like your medical records. Imagine going to the doctor and the doctor says to you, we'll just take your blood, we'll just take your pulse and I'll tell you what's wrong with you. And you go, well, what about my medical records? And the doctor says, oh, don't worry, I can't read those. Well, that's sort of like how we do maintenance. Going back over that history of when was I installed, when was I repaired, what was done, that's really time consuming and difficult to do at scale. And these records, there's a record generated every time a technician touches that piece of equipment, whether it's for an inspection or repair or replace, and it contains structured data like what date it was, and lots of unstructured data like change out the leaking engine, air conditioner not working, and so on and so forth. This data is incredibly valuable, but hidden. And so what we've been doing is making this pipeline, and this is where you'll first start to see the role of ontologies, I hope, is we have a pipeline called maintenance work order to knowledge graph. And we annotate the text, and you can see on the left-hand side of the screen, we use a freely available tool which we've developed and made available called Redcoat. And you can see we have a number of entity classes there. So immediately we're starting to think about not just pulling any old entities out and giving them a word, a name. We're actually thinking about ontologies right from the very start when we do the annotation. We then annotate the text, and you can see in the bottom left, adjust is an activity, belt is an item, drift is a function. These are all clearly the names of classes in ontologies. We use this annotated text to train a deep learning model, which then annotates tens of thousands of other texts for us, which is fantastic because we don't want to do that. And then we store it in a knowledge graph. We use Neo4j, and we can start to do all sorts of things with this. So what the knowledge graph on the bottom right shows you, and the package is called Echidna, and there are demos all over the place on the NLP-TLP site if you're interested, is you can start to see all these different colors, and each of those represents a different entity class, and there's the instance data and the class data and the relationship captured in this knowledge graph. So now is the first sort of role of ontologies in this. You can start to see I have in green a functional location. I can see this functional location has had a number of faults. They're shown in red, and I can see activities against them. But these relationships in the knowledge graph are just based on co-occurrence relationships that occur in the language processing. One of the early things we are working on with ontologies is, are those right? Can we use reasoning to infer whether you would even have a replacement activity on that particular item? So our role, we've been developing a number of modular ontologies. And if you look at the diagram in the middle, you can see in black, I have this downtime event. Yeah, I'm connecting in my knowledge graph maintenance work orders and downtime delay accounting. One of the great things about knowledge graphs is being able to bring different data sets together. I have functional locations. I have an asset shown in the dark green. I have a failure event, an unserviceable code. And what we're doing is we're looking at little ontologies, modular ontologies for each one of these. We're not trying to build an all walking, talking ontology. We've got reference data ontology. We've developed a failure modes ontology that's aligned to a major IEC standard. We have an activity terms ontology that we're working on right now. We have a procedure ontology, and we have a very important and sort of, I think, ontology about the idea of state. What does it mean to be in different states? And we're starting to work on component hierarchies. And the idea is that these are actually all aligned to a top-level ontology. And in fact, I'll go there first. So in our group, we work with two top-level ontologies. We work with the Industrial Ontology Foundry using BFO, but we also work with the Norwegians to use their work on ISO 15926 Part 14. And along with my colleague here, Farhad, we've developed an initial reference ontology, which was done with Haiti back in 2019, and another update of that in 2020 that was published last year. And we're starting to do these application ontologies. And because within each one we're aligned to a top-level ontology, we're beginning to get that sort of interoperability between our ontologies. So you can see each ontology kind of gets to something in the knowledge graph that we want to express or do reasoning over. And just to kind of wrap this up, the huge prize for us, certainly in terms of maintenance work order text, is shown in this example. Say we have a raw work order, replace engine EN001. We tag it with red code. It then gets annotated, and we tag it as an activity, an item, and as engine. Now we pass it into our ontology. You can see under 3 that we've got a replacement activity, subclass of activity, but we've also in the ontology built in the fact that this replacement activity triggers an end-of-life event and that the engine participates in that. So we can infer that that engine has participated in an end-of-life event. And that piece of information is absolutely crucial for something called mean time to failure calculations and for maintenance strategy development. And so this really helps with reasoning over very large amounts of text in order to help automate this process or semi-automate this process for reliability engineers. So I'm conscious of time. We have plenty of references for you, and I'd like to acknowledge the help of a lot of people in this. I'm just like the ringmaster for some really fantastic collaborators. Obviously, the NLP-TLP group at UWA, my colleagues in the IOF Maintenance Working Group are amazing. The Centre for Transforming Maintenance through Data Science, the guys at NIST, the guys in Norway, and of course the fellowship and our industry partners. We are blessed to work with a lot of industry data, and that really motivates what we do. Thank you very much.
Thank you very much, Melinda, also for taking care of the time. So we have time for one question here, but I don't see in the Q&A somebody, but I would like to have one question. So I have this question also for myself. So in the previous slide, you have this text that because your talk is about text. So this one, yes. So so you have this tagged work order which identifies something, replace engine, something. So I assume that this kind of text is in maintenance report, which are written by hand or by computer or whatever. But this text should be formatted in specific way, use specific terminology, or it's free text. So
it's completely, we work with completely free text. So we have done a lot of work in our collaborative annotation to recognize. We can recognize acronyms, abbreviations, all of those things. Yeah, then, we've done quite a bit. We have quite a few publications in that area. It's completely as a mechanic would write it.
Okay, I see. But we will have time to discuss also later. But just to complete, so if the people are using in various reports terms, but with a different meaning, so how we can guarantee that you do the right thing for each one of them?
Yeah, so it depends. So, for example, we know that one of the things we're keen on doing is knowing that certain types of failure modes are very, very unlikely to be observed on certain pieces of equipment. So although a mechanic might write that they see that, one of the things we want to do in the ontology is to flag that that's not a common failure mode. As far as synonyms go, there's a lot of work. The natural language processing community has come a long way, and we find really our models really have quite high accuracy for because we lexically normalize and because we have good understanding of the synonyms that are used by different people when they describe the same thing. Does that answer your question, Dimitri?
I am muted. So thank you very much, Melinda. So there is one question in the Q&A. So or two, maybe you can we can take them at the end, or you can ask them in the chat. So thank you very much. Now I would like to invite the second speaker, so to take care of time, Jinzhi Lu. Jinzhi Lu is a senior research scientist at EPFL, so in my team. He received his PhD in KTH, Royal Institute of Technology in Sweden, in Stockholm, Sweden, in Mechatronics Division in 2019. His research interest is model-based system engineering, toolchain design, and model business system engineering enterprise transitioning. So he is vice head of the China Council on System Engineering in China, and also is also active in the Industrial Ontology Foundry and is coordinating the working group on system engineering. So Jinzhi, please turn on your camera, micro, and Melinda, please stop sharing so that Jinzhi can share.
Okay, thank you, Melinda. Thank you, Dimitris. Okay, so I will. Okay, so can you see my screen?
Yes, Jinzhi.
Okay, so thank you. So today my presentation is systems engineering as the foundation for the industrial domain ontology. And as Dimitri introduced, I'm the researcher at EPFL, and also I'm the chair of IOF Systems Engineering Working Group. So first, I will introduce some background. If we want to develop some complex system, for example, the air engine, we will have different stakeholders for the whole life cycle. Also, we need to have some standards and the process and the business model to control the whole system development process with all the stakeholders. But also, we need to have different enablers for each development process. For example, information to data model knowledge. So how to integrate all this information together, this is a very challenging thing in current industries. So currently, some organization, they provide some, for example, the OMG, they provide some model-based way to trying to define other specification to integrate other information together. So this is one solution. So for that approach, actually they call in the OMG and some engineering domain, they always say, okay, we use the model integration way to describe, to use some specific, to use some graphical model to represent all the CAT model, CFD model, analysis model, performance model, process model, all this information together, trying to describe all the design information in one model. So what we are doing currently is that for model, we are trying to use ontology to represent model. So that's why we have some investigation of the ontology in the MBSE, model-based systems engineering, and the model-based development domain. So we have some data here. So for the last 5 years, the MBSE papers in the scope, there are 1,080 or 900 papers in the scopus about the MBSE and the model-based systems engineering. And we can see ontology for the last 5 years, ontology takes a very important role. For 150 HVE translation and in COSI system engineering journals, we can find that also ontology is a very important, take a very important role in the model-based systems engineering related paper. Also, among 2,000 papers, we can find the ontology ranked the top 1 topic in the digital engineering session. So that means ontology currently for the last 5 years is very important in digital engineering and model-based systems engineering. And we take one example why we want to use ontology to represent our models. So I take one example. In our real world, actually the complex system is a physical system, and it has some abstract concept. For example, the architecture in systems engineering. And we always have some systems modeling language to support the architecture, to describe the architecture. And the modeling language is always used to create different models. And we have different stakeholders, they can develop a different model using the modeling language to represent their information. But the problem is that, for example, the model itself is a virtual event. The physical system itself is a physical event. But the abstract concept is another type of event. I mean, the abstract concept, the physical system, and the models, actually, they are totally different. So in this situation, we should use ontology to represent the physical system, the virtual system, and their concept, some meaning for the virtual system and the physical system. So our IOF is an independent group under OAGI, working to co-create a set of open reference ontology to support the manufacturing and engineering industry needs and advanced data interoperability. And our IOF Systems Engineering Working Group is one of the IOF working group whose mission is to develop systems engineering and model-based systems engineering ontology based on the IOF ontology specifications. And OAGI is an organization to reduce the cost of integration by developing interoperable, cross-functional, across industry, and data model-driven. I mean, it is also an open application group for developing different industrial specifications. So that's why we want to set up a working group to support all these issues. Currently, we have in our roadmap, actually, we have two main streams. The first one is to the IOF systems engineering ontology. We are focusing on the system architecture, system life cycle, and the system requirement, and also system themselves. Another mainstream is focusing on the model-based systems engineering. We hope to use ontology to represent different virtual models. And currently, we have one initial ontology. We call it GOPPRE ontology to represent different system architecture. I mean, different architecture models. We already have several European projects to support to verify our ontology. And I take one example for the IOF systems engineering ontology. For example, in this ontology, we will define the system and the subclass of system. I mean, the social system, the social technical system, engineering system. We also have in the interaction, I mean, how the system interact with each other, and also environment, interface, structure, system boundary, system function, such things. And in model-based, in the MBSE ontology, actually, we capture 6 high-level abstract concepts to represent the model structures, include the graph, object, point, row, relationship, and the property. Using this concept, we can represent the model structures. So this is first, this ontology is developed based on the MOF modeling framework. We construct the ontology based on the meta model, as we can see, because we don't have enough time to introduce other details. So based on the meta model graph referring to some type of window, the whole model. Object reference the model component. The relationship reference the connection between different objects. Row refers to the two ends of the relationship. And the point refers to the port in the object. and the property reference each attribute for all the component. Using this way, we can describe the GeoPPR ontology and transform them in the OWL-based knowledge graph model. So we can use, through this way, we can represent almost all the models using our ontology, like SysML, UML, BPMN, such models. And so I will take one example, how to use our developed ontology to represent the system life cycle or system development process using our ontology. So we have one demo developed in our partner and us. We develop one architecture model to represent the system life cycle. You can see this is a V model for the whole life cycle, but this is a very simple case in order to let other people understand what happened here. So you can see this is a life cycle process. And then when we transform this model, this life cycle model to the ontology, we can generate a OWL model. So when we open this OWL model, we can see all the architecture model is generated in the ontology we design. And then based on these ontologies, actually, we also can reload all these ontologies back to the architecture model. And so you see in all this graph, all this ontology concept, they are generated from the architecture model we show. And so you see this is the individuals to represent all these model components and the interactions between different model components. So through this way, we can represent all the architecture model. Also we can also represent the life cycle of the system. In the future, we will also use the IOF systems engineering ontology to represent each real process in the life cycle. And then in one ontology model, we can represent the virtual model, the architecture model and the system's life cycle, and link them together in order to realize the real world, the physical world, the virtual world, and define the interactions between all these things together. Okay, thank you.
Thank you very much, Jinzhi. So I think we have time also for one question here, but I don't see in the question and answer. So just let me ask you one question. So system engineering, as you say, is a foundational in your title also of domain ontologies.
Yeah.
So I understand that system engineering is not a domain ontology itself, right?
Yes. Yeah. So actually, when we develop the systems engineering ontology and the model-based systems engineering ontology, we consider that actually systems engineering is some type of approach help us to analyze the system in the real world. So that's why we say the systems engineering is the foundation. But the physical world and the virtual world, actually, they are in different domains.
So I see also Eve Kereron is asking in the chat a similar question, and is asking at the end, should we consider it as a formal ontology?
It depends. For the long goal, we hope to create a formal ontology, not only represent the virtual system, but also to represent the physical system. This is the final goal.
Okay.
Yeah.
Good. I think we will continue the discussion also in the end of the session. Now I think it's time, also according to the schedule, to invite Farhad Ameri to take the floor, the screen, and deliver his talk. So Dr. Farhad Ameri is professor on manufacturing engineering and technology at Texas State University and the director of the Engineering Informatics Research Group in FUNIR. His research interests included knowledge-based engineering in design and manufacturing applications, ontology engineering, and design theory and methodology. So Dr. Ameri is coordinating the supply chain working group in the Industrial Ontology Foundry. Farhad, please, I think you shared already the screen. Please go ahead. Thank you.
Okay, great. Thanks a lot, Dimitris, for the introduction. Yeah, it was too late for Melinda in Australia and it's too early for me in Texas. So hopefully my brain will wake up in the middle of the presentation. Yeah, so in my presentation, I'll give you an overview of the supply chain reference ontology, which is under development in IOF. It's not released yet. It's still a work in progress, but I'll give you a sneak peek of where we are. And at the same time, I'd like to give an overview of the procedure that we are using for ontology development, because it's a new experience and collaborative ontology development is a challenge. And so that's a new area for us. First of all, why we need ontologies for supply chains? There are a wide range of software applications being used in supply chains, including ERP solutions, CRM, CSM, e-business applications, semantic web services. So these software pieces need to interact and communicate. And obviously, interoperability in this heterogeneous environment is a big factor, and that's where ontologies come in. There are lots of ontologies, in fact, for supply chain. If you go to like Google search and actually do a search on ontologies for supply chain, you'll find a lot. But still, the interoperability problem in supply chain is not resolved. There are several issues that contribute to this lack of success. One is, in most supply chains, a static view of supply chain prevails. So flow of materials and information is not formalized adequately. Most of them have limited scope, not built for reuse in different contexts. So sometimes taxonomies and class structures prevail. We don't see a real formal ontology with axiomatic nature. And also, some ontologies are just developed to improve communication among humans, but in reality, ontologies should improve communication between machines. And well, a lot of them are not built based on principled methodologies, so it's very difficult to reuse them. That's why we see the gap here. So the objective of the supply chain working group at IOF is to develop a set of modular and reusable supply chain reference ontologies for various stages of supply chain life cycle based on principled methodologies. And those stages are planning, sourcing, executing, delivering, and returning. So these are the standard or typical phases in any supply chain. So in IOF, we really rely on use cases to define the requirements for us because we don't want to develop ontologies in our labs and in the vacuum. So that's why we need to have some use cases. So right now we have 3 use cases. One is related to supplier discovery, the other one supply chain traceability, and third one is logistics. And you can see some terms and notions that we care about. For example, on supplier discovery use case, we'd like to formalize what are functions, capabilities, resources, and the skills and potentials of different suppliers that will become part of a supply chain. Or on traceability use case, flow of material, tracking events, containment, sites, locations, ownership and control. These are the notions that we care about. And on the logistics use case, things like the state of a shipment. Is it damaged? Is it in transit? What's a logistic unit? What's a batch? What's a load? Consignment, identifiers, logistic processes, and routes or special regions. These are the notions that motivate our work. In terms of architecture, we kind of use the same architecture that all other ontologies in IOF are using. We use a top-level ontology, which is BFO for us, and a bunch of mid-level ontologies, including IOF core, and then we develop a reference ontology that provides the ontological constructs for representing a static view or dynamic view of supply chain. And hopefully, application ontologies can be developed through extension of the reference ontology. And it kind of shows the hub and spoke architecture that Barry Smith presented the other day. So on procedure side, so when we define a term, we really would like to start with external definitions, like, because in industrial domain, there are lots of standards. So when you go to ISO standards, we go to APIX or GS1, these are supply chain standards. For each term, we'd like to first understand what's out there, what are the existing definitions, because we don't want to reinvent the wheel, obviously, and then do linguistic analysis on the existing definition, and then do ontological analysis. Hopefully for each term, we'd like to have natural language definition, semi-formal natural language definition, and first order logic definition. So that's because we want the ontology to be useful for both human and also machines. So on ontological analysis, depending on the nature of the entity, will have different levels of complexity. For example, plant process is an example of a class that needs very careful analysis, and we need to look at this from different perspectives. For example, what are the primitive processes used in that plant process? What are the agents involved? What are the process parts? Or what are the objectives, plan specification, location? So these are the dimensions that we need to look at. And we try to use Jira. Jira is kind of a task or issue tracker under Confluence. And it kind of facilitates the workflow and the analysis process. So that's the tool set we are using in IOF. And we always prefer to have first of all, use case, then a set of competency questions and external definitions. These are the prerequisites before we can start the term analysis. So we use this checklist before, for example, if you want to analyze manufacturing service, so what's the use case in which this term is being analyzed? What are the competency questions that we care about? And what are the external definitions that we have extracted from existing ontologies, existing standards? So again, we use a modular architecture. So BFO and IOF core are kind of the standard ontologies that we import, but depending on the nature of ontologies, there might be several smaller or mid-level ontologies or domain ontologies that we'll import. So can you hear me? There's some noise coming in. Anyway. So, but for example, supply chain structure ontologies uses organization ontology that itself will import skill ontology, business function ontology, industrial capabilities ontologies. They don't exist yet, but that's kind of the vision that we are hoping for. Right now, the supply chain reference ontology, it has basically a few ontologies inside of it. I'll focus on agri-food traceability use case just to give you an overview. So food traceability is the ability to trace and track a food product through specified stages of production, processing, and distribution. So we use ontology for standardization, data integrity, semantic integration, and reasoning for history exploration and discovery. So for example, traceable resource unit is a type of class that is basically a role borne by object or object aggregate when they have a shared history and some agent have interest in retrieving the information. Or tracking event is a type of occurrence, and in general, event is a very challenging term to define, but tracking event is a type of events that we care about in supply chain traceability. Container and container role. So we define role for a container, for example, such that we can have a tabletop play a role of a container. So roles are the patterns that we use a lot. So these are just some examples of the basically the classes we use in supply chain in traceability part, and in interest of time, I'll just go over them quickly. So we validated the ontology using some simulated and real data from harvest to on-farm storage use case, and we created RDF triples, and we created a tool to visualize the triple. In that way, we can really do the traceability process much easier because we can actually see the sequence of operations in the supply chain. So that's my last slide. So obviously it's not an easy process, especially if we are working with such a vast area and like to address different type of use cases. So come up with the strategies for modularization. Right now, the reference ontology is a single monolithic ontology. We need to break it up to modules. So what's the strategy for modularization? Where is the cutoff line between reference ontology and application ontology? Sometimes it's not very clear. We need more efficient ways to use tools for using ontology design patterns, so that we have not been very successful there. More use cases and data sets to cover entire domain, and also we need more participation from domain experts. So if you're expert in supply chain, we invite you to attend our meetings and help us. And with that, I conclude my presentation. Thank you.
Thank you very much, Farhad. So if you want to stop sharing your screen so that we see all the participants. Thank you very much. So now we have some questions also, but related to the whole, let's say, purpose of this session about domain ontologies, and also with regard also to life cycle, as it was highlighted in the system engineering. But I would like before to have a question for you, Farhad, and the for the supply chain ontology. So what are the challenges in developing a unified model for supply chain ontology? And how, let's say, to this unified model, how could we establish its relation of this ontology of supply chain to manufacturing operations, if you can say a few words about that?
Yeah, I mean, one challenge is that we have a lot of stakeholders involved, and they have their own viewpoints and perspective, right? So to have a unified ontology that addresses varying perspectives, that's always a challenge. And well, we hope that using a top-level ontology will solve the problem, but at some from one aspect, like forcing a single viewpoint through a top-level ontology might become problematic. But it will give us some rules, some structure, some way of thinking and modeling. So we hope that using top-level ontology will address some part of the challenge. And then the second part of your question was relating it to manufacturing operations. Yes, we have internal supply chain and external supply chain. When we go to internal supply chain, we talk about the internal manufacturing operations of a company. And so basically, they are the same entities, they are processes, but within different boundaries. So we try to model processes no matter where, if they are inside a manufacturing organization or outside, and then try to link them appropriately.
Good, thank you. So now I think we can go a little bit to the discussion of the whole session. So there was a comment in the question and answers about what you said, Farhad, from Emmanuel, I think, yes, about ontologies as primary machine-oriented tools. And the thing is that how we can consider ontologies also as a kind of enabler or a kind of tool that can enhance interoperability between people as well. So yeah, so this is I don't know if you see the question. What do you think about that? So, and now also it is highlighted that this is a topic of Industry 5.0, where human is at the center of the operations activities, industrial and other activities. So I understand from Emmanuel's point that we need technologies to enable interoperability between people. So what do you think? So can ontologies play this role, or should remain, let's say, as tools to enable interoperability between machines? And machines, I mean software that are serving machines.
Can I have a go on that? Or?
Yes, please, of course.
Yeah, okay, sure. Yeah, so yeah, in fact, yeah, exactly. That's really something we need. A human in the loop is required. The problem with some of the ontologies that we have seen is that they are mainly designed for human, ignoring machines. So we say, okay, now we should have human and machine together. That's why in our definitions, we'd like to have human-friendly natural language definitions. We would like to involve human experts, such that, first of all, humans are the main users of the ontology. So the definitions should make sense for them first before we can formalize them. So I totally agree with Emmanuel, and yeah, human role is very critical here.
And then another question, which is, I think, related to that, is as we see also in system engineering and in standards and the discussion that we have. So we have different viewpoints, and particularly in also in the domain supply chain, but also in maintenance. So where I have some experience, we have various different viewpoints, and we need to integrate them. How this could be, let's say, addressed in a domain reference ontology for maintenance, for example. So I mean, the need to integrate different viewpoints, and as we discussed in the previously, so this situation that people define terms in different words or in having something different in mind.
Okay, so sorry.
Maybe Melinda, you can start.
Okay, so I think this leads to a huge amount of confusion. Often people define things differently, but it's in fact a part of their background or training, and this creates enormous confusion. And one of the great opportunities, particularly in something like failure modes and effects analysis, is to move away from people's loose use of terms when they describe things. And by taking a richer set of terms around that, we can nail into the concept they actually mean and map it to the physics. And to take the words that people use to describe something, like, I can't turn this and it's stuck, all map to a concept of fail to open, which is an ISO 14224 standard. So the challenge for us is to actually add clarity and conciseness by using reasoning to remove the ambiguity caused by the language used by different people. So I think this is a huge opportunity, and we're working in this area. We have a limited number of failure codes that really are discrete. They're broadly orthogonal to each other. But if you look at the failure mode codes that companies use, there are like 80 of the things, and most of them are duplicates and not clearly just differentiated. And so people do a lot of work with those failure codes. They spend enormous amounts of money doing Pareto tables and tracking things, but most of them are wrong. So getting those right and clearly differentiated, regardless of the background or semantics of the people used, is a huge opportunity for ontologies.
And I think how we can do it.
We are working on that. So part of this is
yeah, I know.
Go on.
But it's yeah. What I was thinking is that in order to implement an ontology or to design an ontology, I don't know what is the correct term here. We have to pass through a process of defining terms through a natural language definition between experts, subject matter experts as SMEs, that not small and medium enterprises, subject matter experts, and knowledge engineers or ontologists. This process takes time, but I understand that it is crucial before we go to the formal definitions using FOL or CL or OW or whatever. I think that this process, this phase of ontology development, this dialogue between people to agree on a proper definition in natural language is very important. And I think this is a step that help helps the interoperability between people as well. So
yeah, so Dimitri, all I would say is that we've been doing this for 3 years in the iOS, and as far as I can concern, we just go round in circles. So at some stage, we have to move away from coalescing everything on a simple term, and everybody new comes with a different definition, and we have to take into account both the class and its relationships to define a concept. And that is, you know, just defining the term by itself is not enough. You have to define the concept and the relations around it, and we should spend more time doing that.
Mm-hmm. Very good. Then there was also in first comment by Eve, and then I asked somehow also about the system engineering ontology, which could be a formal ontology. By formal ontology, I understand that it should be a middle-level ontology used by other ontologies also. And in my understanding, so here we have the examples of a maintenance ontology and of a supply chain ontology. And in my understanding, these, let's say, tools, these models, are applicable to particular or phases of the life cycle of a product. So my question is how, let's say, a system engineering ontology, which is defined here in the talk, in the title, as a foundational ontology, what is the role of such a system engineering ontology? Is to be in a kind of upper level of domain ontologies and help to link applications and models used in various phases of the life cycle? Is that something that we consider, Jinzhi?
Yeah, I think the first thing from the systems engineering domain, actually, in systems engineering domain, systems engineering or system thinking is an approach for the engineers how to consider, how to see the world. So that's why when we use systems engineering or system thinking, we use such framework or such approach to formalize the real world. So that's why I think maybe if it depends on how we treat the systems engineering ontology. I think maybe we can put them in the middle in the domain, some type of high level ontology. But this is not from the ontology engineering. This is from the systems engineering way, because we have different approach to see the world. So yeah. But actually the nature of the world, actually they are the same. So yeah.
And also in your talk, you also talked about model-based system engineering ontology. What is the difference between a system engineering ontology and the model-based system engineering ontology?
Yeah, so that's why just as I introduced, I take one example is that, for example, there's one company who wants to develop one pencil, and they have their own CAT tool. For example, they have their CAT tool. They use the CAT tool to develop the model for the pencil. So sometimes, for the people in the company, they always think, okay, the pencil and the model of the pencil, they are the same. But in fact, actually, they are different. So model-based systems engineering ontology is used to represent the model. I mean, which represent the system. So which represent the physical world. And what we want to say is that the model and the real world, the real world and their model, actually, they are totally different things. So that's why I want to say the model-based systems engineering ontology is some type of ontology to represent the architecture model, the graphical model of this system and the systems engineering perspective.
So the technicalities of the model, let's say, using, nodes, links, relations, etc. This is what you mean.
Yes.
And to automatize something, somehow this works. Very good, thank you. So we have an interesting question from Peter Klein now, who brings into the discussion the topic or the concept of which is popular, so emerging concept of digital twins in manufacturing. And also you see the I think I don't know if you've seen all your screen, and how it is related with edge computing and or cloud computing, and how digital twins are, let's say, linked to domain ontologies. For example, we may have a digital twin for a supply chain solution or a digital twin for maintenance. So there is a lot of also in the market, let's say, products or solutions claiming to sell digital twins for predictive maintenance, for example. So, and this question is for all the presenters. So let's take first Melinda with this digital twin for predictive maintenance. What do you think? So how ontology can support the digital twin for predictive maintenance?
Don't get me started. Yeah, my God, it's a mechanism for consultants to earn vast amounts of money. So, you know, I replied to Peter in the chat. I interpreted his question in a slightly different way. I mean, I think the digital twin itself needs maintenance. You know, if you have a model and you have a physical thing, they both need maintenance. So you just use the maintenance domain ontology to manage
ontologies need maintenance as well, Melinda.
That's right. That's right. So I think we've had digital twins forever. You know, process plants have had simulations for forever. I have yet to see any really substantially good examples of predictive maintenance digital twins that really work in the way that I think they should. So I'm not worried about that at the moment. Give me a working predictive maintenance digital twin that's used by an industry partner as part of maintenance management and tied into their work order system, and I'll pay attention. But until I see one, and I haven't yet, I'm not worried about it.
Mm-hmm. Farhad, what do you see in the supply chain, let's say, market or communities? Is there a discussion using digital twins or applications of digital twins there?
Yeah, so there are some emerging models of like digital twins for supply chains, but they are not being used very extensively yet, to the best of my knowledge. But well, it's all about how you model data that is actually coming from digital twin. So it's not, in terms of ontology, it is not really adding a new challenge to this whole problem statement we have. We still have a set of data that needs to be represented using or aligned with that ontology. So a digital twin for a supply chain will have, for example, some timestamp. So how to model time or temporal regions it's the same problem. So it doesn't really impose new sets of problems. It's just kind of larger in a scale, because a digital twin should be a comprehensive model of a supply chain, and that's why we are working with larger scale data, very diverse data. But the type of ontological modeling challenges are not necessarily different, because at the end of the day, we are still dealing with data. So that's my take.
Mm-hmm. Good. Thank you. And Jinzhi, I will come to you with the next, let's say, part of answer to this question. So digital twins are, as you, I think so, in your one of the first slides, or if you take the life cycle, design, production, maintenance, or use and maintenance, and then end of life, we may imagine that we have various digital twins that are implemented to serve, to provide services in the various topics of in each phase of the life cycle. So how about a system engineering ontology or a model-based system engineering approach? Would it be useful to link these digital twins together, or harmonize their operations, or optimize their operations? Or we let's say allow people to use them independently, and then somehow they need to coordinate?
Okay, thank you for this question. Interesting question. Actually, in systems engineering, digital twin, the guy related to digital twin, they have a lot of people, they are focusing on how to use simulation model, simulation tool, and maybe create the digital twin to support some real domain, to solve real domain specific problems. And some people, they are focusing on the develop some framework for digital twins, because just as we discussed, the digital twin, we already have, for the whole life cycle, we already have different computer-based models or mathematical models. And this model already exist. They already exist in the work. So this is not new thing, but why they propose this new concept about digital twin? I think they are focusing on how to use the model to solve the real domain problem. They trying to make this framework, digital twins framework, or this approach to solve the real problem in the work. So that's why they have different frameworks. I think the systems engineering ontology in this case is we can support, as we introduced in the presentation, we can support to describe the interrelationships between the virtual world and the digital and the physical world. In the previous framework, digital twin frameworks, most of the framework they are focusing on how to communicate with the digital twin execution models and the real physical system. But our systems engineering ontology, actually, we can represent the interrelations from a static way, from a formal way. So I think this is the main purpose for the systems engineering ontology to support digital twins.
Okay, thank you. And we have another question for a different topic from Grigoris Menzas. Hi, Grigori, welcome. It's how we see the integration of ontologies with data-driven artificial intelligence approaches, for example, machine learning, in the manufacturing domain. Yeah, you see also here because we have a lot of data. So in maintenance, we have a big data. In supply chain, we have the big data, and there is a community which is called now AI. So there are other communities that try to extend this term and call it explainable AI. So maybe ontologies can contribute to this explainable AI. But the question is how, let's say, we can combine, let's say, machine learning techniques to ontologies. Yes, Melinda.
Okay, so this is exactly what I tried to show in my presentation. We start with text. We use deep learning to process the text to get the knowledge graph. From the knowledge graph, we infer whether we have an end-of-life event or not, and the failure mode associated with that event. That end-of-life event inference becomes the response variable for the machine learning to train the machine learning models. So this is not a future thing. This is what we are doing.
Farhad?
Yeah, in fact, Barry Smith has a paper titled "Make AI Meaningful Again." So I recommend you to read that paper. And it's all about how to integrate ontologies and semantic with AI. Yeah, I mean, they kind of work together very closely, these two topics, because if we can give meaning to data, then we can do more intelligent machine learning. We can do better job as opposed to just meaningless data or numbers. For example, in our supply chain traceability use case, we are collecting data from different suppliers, and they obviously use their own schema and data model. But if we can integrate those data sets, then we have a larger data set to work with, and then we can apply machine learning to a much larger data set, which is harmonized. And the result of the models that we get as the output are more dependable because they are based on a larger set of data that is merged based on an ontology. So yes, it will obviously support if you use semantics and apply semantic models on data and machine learning.
So if I'm allowed to make a comment also, in my knowledge, some current machine learning techniques and algorithms are working on raw data, and they try to learn from patterns in raw data and learn or create knowledge from raw data. In some domains, they are successful. In the engineering domain, in manufacturing, and more generally in the engineering domain, I think we have to go beyond zero numbers, go to the meaning of data. And what we have with ontologies, if we, let's say, use an ontology to create a knowledge graph, in this knowledge graph, we have the instances, so the individuals, together with the relations. And I know that there are some communities. I know one, for example, in the Technical University of Vienna, where they try to apply or to extend machine learning techniques to work on knowledge graphs. I mean, data that are linked with relationships, big data linked together, and develop machine learning techniques on this kind of semantically structured data. So I understand this is work in progress, but I think it is in line or along the lines of the paper of Barry Smith that Farhad mentioned, make AI meaningful. And I personally expect that there will be progress in that direction. We have also one question from Hedy, which says that, I will read it. We can have agreement on terms used in the domain ontology, but what about agreement on the interpretation of those terms and relationships between them? Conceptualization. This is defined as conceptualization. Do you believe that in pluralism within the industrial domains? I think pluralism, that we are allowed to have different interpretation of those terms.
Very dangerous for an engineering. So, do we really, in engineering school and in businesses and in the Air Force, or in critical or in space, do you think people will go, oh, it doesn't matter, you can call a centimeter an inch? No, we don't do that. In engineering, I don't think it's like being in the arts. I don't think it's like theatre predictions. In engineering, we need to agree within the context of the terms we are using them, what their meanings are. And I think if you work for a company, we already have corporate type languages. We're quite firm on that. So I think if across domains, you might have different interpretations. If I go to aerospace, there will be a different culture and language there, but I think immediately you start to accept that you can have many different ways of describing things in an engineering concept around equipment, I think you're just asking for trouble, and the risks are horrible.
Yeah, I agree with Melinda, especially if you expand the domain of the ontology, the scope of the ontology, and it's includes different organizations, different stakeholders. If you don't have a unified definition of a term in a reference ontology, it would be very difficult to use the same reference ontology for multiple use cases. But suppose that you are within a company and you just want to develop an ontology for your own application. Yeah, that's okay to have your own interpretation, and which does not agree with other organizations. But as a reference ontology, then you really need to have a really clear agreement on what you mean on each term, formally and informally.
Can I just mention, Dimitris and Farhad,
yes.
That's why we have standards. Do you know what the very first page of a standard is? It's a definition of terms. Everything you read in this standard in engineering has this definition. So this is the world we live in. We live in a world of standards. We live in a world of clear definitions. We don't live in a world of, I just want to be somebody else today, and that's okay.
Good. So I see a comment from Farhad here with regard to system engineering ontology. Farhad says that supply chain is an engineered system, and as such, so it needs to be connected with other elements, and the system engineering ontology is necessary, critical and necessary. So Jinzhi, so I remember that we discussed in the group a lot about engineered systems and other systems, for example, natural system. So can you tell us a little bit about the engineered system and what is the focus of the system engineering ontology? Is it really on the engineered system or more generally in systems?
Yeah, I think currently in our systems engineering working group, the system we mentioned is much more focusing on the engineered system. I mean, some man-made system. So, but still, the systems engineering ontology we are still developed. I mean, the ontology is still under development. So that means we need more discussion to find more way to extend our current ontology. So, what I can say is it is very challenging to use the systems engineering ontology with some other domain specific ontology currently.
And how yeah. If we take if you allow me to go a little bit further, so if we take the supply chain, so which is an engineered system, but as such, a supply chain is using elements of natural systems. For example, the environment. If you take a ship that transports containers in a supply chain or a truck, so this is using the sea, which is part of the natural system, or the truck using the atmosphere or something, which is part of the natural system.
Yeah.
So it is necessary or required to have these links between engineered system and natural system.
Yeah, I think yeah, of course, I think this is very important because from the systems engineering approach, actually, when you define the system, that means you need to define the system boundary and its environment. And because of the environment, then you will have some input to this system. I take one example is the sea. I mean the salt water and the water actually they are totally different. I mean the sea and the lake they are different to the ship. On the perspective of the harm to the surface of the ship. So that's why I think the natural system and the engineered system is very important to identify the interreactions between them.
Very good. And also I see that in the chat, so there is also some comments about symbols, because so we discussed it here about terms, but in the engineering domain we're using also symbols. For example, in drawings we have symbols, or also we have some other elements, for example sounds or smells that I see here also. So how we can let's say include this kind of let's say entities or physical matters in ontologies, transform them to text definitions. Yeah, Melinda?
Yeah, so I mean, I think of these as just being attribute values and attribute.
I saw that I read that you define them as artifacts, so they can be defined.
Yeah, so but they're attributes. A motor makes a sound, and it's an indication of a problem. But the sound is measured with a meter, and the measurement itself is a value, and it has a unit. So all of these things are standard classes in ontologies. So I don't see that. And the PNID symbol one to me is a PNID is a tag. It goes back to what there's a coding system that describes what sort of equipment it is. It's in a CAD drawing. It's actually text. It looks like a symbol to us, but behind it, it's a tag. It's got a text. It's got a number. It's interpretable.
I think I agree with you.
Yeah.
Drawings have a lot of symbols, which is a kind of language. For example, in drawings, you have a lot of symbols about tolerances, and tolerances are clearly defined in, let's say, in the documents, etc. So it's a kind of language that can be also defined, I think, etc. Very good. And then in terms of standards, we talked about standards. So one of the contributions of Ontology Commons project and also the Industrial Ontology Foundry is to contribute to good definition of standards. And I know, and I think you know also, that there are standardization organizations and communities that they try to somehow transform they are standards somehow in ontologies, or use ontologies to describe their standards. Or even there are corporations that what they do, they have a number of standards that they are using, and they have teams that they transform these standards to ontologies in order to implement them in applications, in their operations, etc. So my question is, what do you think? What is the role of ontologies, and particularly communities such as Ontology Commons or IOF, to the next generation of standards? So yesterday I heard the term smart standards. So will ontologies be useful to make standards more applicable, more useful, better, let's say, contribute to the interoperability among people, finally?
I'm happy to have a go at that. Dimitris has long been something that ever since I got involved with ontologies, because I have quite a long history with the standards community, because I was on the ISO 55001 committee. And it's immensely frustrating to me that ISO itself has vastly different definitions for its terms across its standards. In maintenance, it's chronic. There aren't two standards that define maintenance the same way. And then if you add in IEC and IEEE and ANSI, it would be great actually for the ontology community, the engineering community, to get together and to agree to align just their terms and definitions. And I think ontologies could find where the problems were, the most egregious problems, where things were most semantically different, and could then encourage the higher level JTCG type groups to actually align those. And ontologies would be a great way, but you'd need them on board because you need to import all their documentation, process it, and then work out where the major disconnects were between the terms and definitions used in the standards, and have one set.
Yeah, and what can I add is that there are two different artifacts. Like ontologies cannot replace the standards. We still need the standards because in a way they need their own context. So so what we can use standards to inform ontologies, to provide us with definitions. And also we can use ontologies to annotate the standards. Maybe in future we don't want to have PDF files for standards. If we go with model-based systems engineering, maybe standards are represented in more machine-readable fashion, and then we can use ontologies to annotate the standard text, for example. But my point is that there are two different things that they can support each other.
Jinzhi, you want to say something?
Yes, and I think currently from the systems engineering domain, for example, SysML, in maybe 20 years ago, they hope to create some graphical specification in order to realize the unified description for all the engineer systems information. And now they already changed this graphical specification back to the semantics way, I mean SysML 2.0 such thing. So I think maybe in the future, if we can, based on the ontology, we can develop some open source software which can be used to represent the ontology model. I mean the ontology model or ontology specific based on some ontology specification that will be used for the future. This will be very helpful to make the ontology used in the real industry. I take some example. For example, if we provide different domain ontology specification and different domain ontology model library, and then we have some open source software which some other people, they can use this software to manage their own knowledge, to create their own knowledge model. So I think this will be much helpful.
And also from my experience in IOF so far, so I observed that when we try, let's say, start with ontology, we are a group of people, so ontology is subject matter experts, and we try to define or to write down definitions of terms. So we try to see if there is a definition of a given term in some standards. And in, for example, in system engineering working group, so for one term, we find 5 or 3 or 4 definitions for each term. So maybe the work also, the process of developing ontologies in the industrial domain may help to align standards in this same domain. And then there will be another process of how standardization organization can work with that. But I think let's go step by step. So I think we are approaching the end of this session, but I think if we, I would like to clarify this point of that Eve raised. So, Eve, can you, if the managers can open the micro of Eve Keraron and explain, allow him to express his opinion? I can see if I can. I don't know how to open the micro.
Hi, Dimitris. Can you hear me? Yeah,
yeah.
sir. No, I'm inviting Eve on stage. It's just my computer was a bit slow.
Yeah, sorry. Yeah, if you will be invited on stage and then
yes,
and contribute. Yes, we hear you, Eve. Please.
Yes. First of all, thank you very much for the presentations and the exchanges we have. Actually, the point I mentioned was there is a lot of standards in industry already to make interoperable physical plants and products. They are interoperable. The point is that intellectual information systems are not interoperable. And what I was highlighting is that there exist many standards, like standards on symbol for PAN ID.
Hi, Eve, in case we cannot hear you at the moment, so maybe you need to authorize the microphone for the platform. There should be a pop-up, and you should click on authorize for the mic and video.
I think I don't see the authorize. But
I can hear Yves.
Yes, I can hear you.
Okay.
Now, yes.
Okay.
Yeah.
Thank you. Somebody in the chat also mentioned S1000D. It's about tech data for every kind of civil and military aircraft, or S2000M, and there are many interesting standards with big efforts made on conversions on terms, concepts, properties, and so on. And I think we have not to start from zero. We have to start from all these standards also, and all the habits of industrials to share knowledge. PAN ID is a very efficient way to communicate, and with links with common understanding of symbols and things like that, and so I think we don't need to begin from scratch, but and also to valorize all the existing knowledge in industrial business standards.
Very good. Any comment to what you've said? I think I cannot agree more with that. So standards are let's say, long-term process, and in order for a community to arrive, a group of people to arrive to a standard, and this be published by ISO, for example, there is a long process of iterations, votings, etc. So there is a lot of value of it, and of course, it has to be valorized. Yes. And I think semantics and ontologies, all this process at least, may help this process to become more efficient, I hope.
Yes, the question is to digitize these standards, probably. and ontology can play a role, of course.
Exactly.
But maybe it's an enabler, but maybe not the only one. We need also methods to transform textual requirements in informal requirements and things like that. So
yeah.
Okay, thank you.
Good. So we have 4 minutes. So I would like to invite, let's say, the speakers for 1 minute or so to say their final word before we close for lunch break. So Melinda.
A wrap up, Dimitris. You've caught me by surprise.
Yes, let's say a few seconds to say your final word. So.
Okay. So look, I maybe, given this is the IOF session, I think that it would be great if the speakers on the call, people who are listening, if they want more information about the IOF, we have a website, we have domain working groups. Most of us have private Git sites, we have active meetings. And I think that if you're interested in ontologies, this is a great way to both keep in touch with stuff that's starting to move quite fast, as well as hopefully contribute. So I'd encourage you to reach out to the IOF community and get involved, please.
Thank you, Melinda. Farhad?
I'd like to mention that it's a huge challenge. I mean, the domain is vast, right, in industry, and we really don't have answer to all questions. We just need to experiment and practice and fail. So, for example, one big question is a foundational approach the right approach? Well, we don't know yet. Maybe we just have, for example, one experience from biomedical industry. So, and it was successful. Will it experience the same level of success in industry? Maybe yes, maybe not, but let's give it a try. And as a community, let's just be open to that foundational approach, and we'll use IOF as a platform for that. If we fail, hopefully we learn something, but let's try and let's get something out.
Good. Jinzhi?
Okay, so I think systems engineering is some method which can be foundational method which can be used to define the ontology for different domain concept. But this is not the only way. But I think from our perspective, maybe this is one of the most interesting way we can try to realize to use ontology to represent the domain-specific concept. So I think if someone who interested in this topic, maybe you can join in our working group meeting to discuss with ontology with using systems engineering approach and use your own domain specific approach. Okay, thank you.
Thank you, Jinzhi. And with that, I would like to thank all speakers, Melinda, Farhad, Jinzhi, for their contribution to this session, and also the Trust IT staff for the organizing and the taking care of all the technical aspects, running it well. So now I invite you, and I wish you to have a very good lunch break in your place. Unfortunately, we cannot offer you lunch this time, but we really hope that before the end of the Auto Commons, we have the opportunity to meet in person in the next global workshop, and then smell each other, Melinda, and then feel well. Thank you. Goodbye. See you in the afternoon.
Goodbye. Thanks, everyone.
Bye bye. Bye bye.